Over 2,000 years ago, in the ancient Greek city of Syracuse, a brilliant thinker named Archimedes asked a simple question. Why do some things float while others sink? If you like similar educational content, please like the video, subscribe to the channel, and share the video with your friends. He wasn't just a mathematician. He was an inventor, a physicist, and a curious observer of nature. According to legend, King Hiero asked him to find out whether his golden crown was made of pure gold or if the goldsmith had secretly mixed in cheaper metals. Archimedes puzzled over this problem for days. Then, while taking a bath, he noticed something fascinating. As he stepped into the tub, the water level rose and spilled over the edge. At that exact moment, it hit him. The volume of water displaced equals the volume of the object submerged. He jumped out of the bath, ran through the streets shouting, "Eureka!" which in Greek means, "I've found it." And just like that, he discovered one of the most important principles in physics, Archimedes' Principle, the rule that explains why ships float, why icebergs don't sink, and how submarines dive and rise again. The core idea of Archimedes' Principle. Archimedes' Principle states, any object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid displaced by that object. In simple terms, when you place something in water, the water pushes upward with a force that depends on how much water is displaced. If that upward force, the buoyant force, is greater than the object's weight, it floats. If it's smaller, it sinks. Density, volume, and weight. The relationship buoyancy depends on two key things: the density of the fluid and the volume of the submerged part of the object. That's why a small steel nail sinks, but a massive steel ship floats. The ship's overall density, steel plus air inside, is less than the density of water. This single principle connects mathematics, physics, and engineering, and it became the foundation of hydrostatics, the science of fluids at rest. To truly understand how Archimedes' Principle works, we need to look at what happens inside the fluid when an object is submerged. Water isn't empty space. It exerts pressure in all directions, and that pressure increases with depth. Why water pushes up. When an object is placed in water, the bottom of the object experiences higher pressure than the top because it's deeper. This difference in pressure creates a net upward force, and that's exactly what we call buoyant force. The fluid literally pushes the object upward, trying to reclaim the space that the object is taking. This invisible force is what allows things to float or feel lighter when submerged. The equation behind buoyancy, Archimedes' Principle, can be written as buoyant force is equal to fluid density times gravitational acceleration times displaced volume. Each element of this formula matters. Fluid density. The denser the fluid, the greater the buoyant force. That's why you float more easily in salt water than in fresh water. Gravity. The stronger the gravity, the stronger the buoyant force. Displaced volume. The more fluid an object pushes aside, the greater the lift. This simple relationship determines whether something floats, sinks, or hovers in a fluid. Why a steel ship floats, but a nail sinks. Steel nail is small and dense, so it displaces only a tiny amount of water, not enough to balance its weight. It sinks. But a steel ship is full of air-filled spaces. Its total density, metal plus air, is lower than water's density, so it displaces enough water to generate a buoyant force equal to its weight. That's why a massive ocean liner floats while a small nail sinks. If the ship's hull gets damaged and fills with water, its density increases, the buoyant force is no longer enough, and it sinks. Ice and water. Nature's balance ice floats because it's less dense than liquid water. Roughly 1/10 of an iceberg stays above the surface, while 9/10 remain hidden below. If ice were denser than water, oceans and lakes would freeze from the bottom up, and life as we know it would not exist. Archimedes' Principle literally keeps the planet alive. Buoyancy in air and gases. The same law works not just in water, but also in air. That's why helium balloons rise and hot air balloons lift off. Helium balloon. Helium is lighter than air. Upward buoyant force wins. Hot air balloon. Heated air becomes less dense. Buoyant lift increases. Even submarines and blimps use this principle. By controlling the amount of fluid or gas inside, they can change their density and move up or down. A universal law, Archimedes' principle, applies anywhere in the universe. If there's a fluid, liquid or gas, and gravity, there will always be buoyant force. From ancient baths to interplanetary probes exploring methane oceans on Titan, the same law governs how things rise, float, or fall. Archimedes' principle isn't just an abstract formula, it's something you can see, test, and experience with your own hands. From a child playing with water to a submarine engineer calculating ballast, the same physical law governs it all. Simple experiment. Seeing buoyancy in action, take a bowl of water, a stone, and a piece of wood. Drop the stone in, it sinks immediately. Place the wood. It floats. Now push the wood completely underwater and let go. It shoots back up. That's the buoyant force pushing it upward. If you hang the same block of wood on a scale and then submerge it in water, you'll notice it weighs less. That's because the scale measures weight minus the buoyant force. The difference between the real weight and the apparent weight is exactly the weight of the displaced water. This simple experiment perfectly demonstrates that water really does push back, and buoyancy is real, measurable, and predictable. Measuring density with Archimedes' principle. Archimedes himself used this method to measure the density of solids. Here's how it works. Measure the object's weight in air. Measure it again while it's submerged in water. The difference equals the weight of the displaced water. Since the density of water is known, you can calculate the object's density by comparing its mass to the displaced water. That's exactly how Archimedes discovered that King Hiero's crown was not pure gold. It had a lower density, revealing it was mixed with silver. Ships, submarines, and floating structures. Without Archimedes' principle, there would be no maritime industry. Every ship, from a small fishing boat to a giant tanker, is designed to displace exactly as much water as its total weight, including cargo, fuel, and crew. Ships have a plimsoll line, showing the safe maximum draft, how deep they can go. Submarines adjust buoyancy using ballast tanks. When filled with water, they sink. When emptied, they rise. Offshore platforms, bridges, and floating turbines rely on the same principle. A discovery made in a bathtub now governs the oceans of the world. Buoyancy in air. Balloons and blimps. Archimedes' principle also applies to gases. Air, though invisible, behaves like a fluid. A helium balloon rises because helium is lighter than air. The air beneath pushes it upward. A hot air balloon lifts off when the air inside becomes warmer and less dense. Even airships, blimps, and weather balloons use this same logic. They float because the upward buoyant force in air is greater than their total weight. The principle doesn't care if it's water, air, or methane on Titan. It simply works anywhere. Density and gravity exist. Amazing facts about buoyancy. Only about 10% of an iceberg is visible above the water. The rest lies hidden beneath. In the Dead Sea. You can float effortlessly because the water is incredibly salty and dense. Astronauts train underwater, using buoyancy to simulate microgravity conditions in space. From simple childhood experiments to high-tech engineering and space training, the same law of physics connects them all. More than 2,000 years after its discovery, Archimedes' principle still shapes the modern world. From the way we build ships and submarines to how we explore space and understand the human body. It's one of those rare physical laws that connects ancient wisdom with modern innovation. The foundation of engineering and design. Every floating bridge, tanker, and oil platform relies on Archimedes' principle. Engineers precisely calculate how much water must be displaced to support the structure's full weight, including cargo and crew. Today, advanced computer simulations combine this ancient law with hydrodynamics and fluid mechanics, to design vessels that can withstand storms, waves, and shifting currents. Without it, there would be no modern shipping industry, submarines, or floating wind farms. A law discovered in a bathtub now underpins some of humanity's largest machines. Archimedes and space exploration. You might not expect a law about water to matter in outer space, but it does. NASA uses giant underwater training pools to simulate weightlessness. Underwater buoyancy helps astronauts learn how to move as the upward force of water partially cancels their weight, mimicking the microgravity of orbit. When designing probes for other worlds, scientists use Archimedes Principle too. For example, future missions to Titan, Saturn's moon, must calculate how their landers will float in liquid methane, applying the same math that Archimedes used over 2 millennia ago. The principle of buoyancy even extends beyond Earth. Wherever there is a fluid and gravity, Archimedes' law holds true. Buoyancy and the human body. Archimedes' principle also explains why you feel so light in water. When submerged, your body is pushed upward by a buoyant force that makes you appear to weigh less. That's why swimming and aquatic therapy are so effective. The water supports part of your weight, reducing stress on joints and muscles. This ancient law doesn't just move ships, it helps heal people. Nature's hidden balance. Nature has used Archimedes' principle long before humans discovered it. Fish use swim bladders to control their depth. They adjust the amount of air inside to change buoyancy. Ice floats and protects the life below. Birds and insects exploit tiny density and pressure differences in the air to stay aloft. Even clouds, vast collections of water droplets, float because their average density is lower than the surrounding air. From the deepest oceans to the highest skies, the balance between gravity and buoyancy keeps the world stable. The legacy of Archimedes. Archimedes wasn't just a mathematician. He was a philosopher of nature, one of the first to believe that the universe follows logical, measurable laws. His discovery marked the birth of experimental physics, a moment when observation and reason replaced myth. Today, when a ship sails, a balloon rises, or an astronaut trains underwater, it's the same ancient principle at work. Archimedes' principle is not just about physics. It's about balance, between weight and lift, between earth and sky, between curiosity and discovery. Conclusion: from a splash in a bathtub to the oceans of space, Archimedes' principle reminds us that even the simplest observations can lead to discoveries that change how we understand the world. Sometimes, all it takes is a curious mind and a bit of water spilling over the edge.